not water, not ancient rivers, not even habitability. For decades, scientists have searched Mars for something far more specific. Not landscapes, not environments, but a signal. Something that should not exist unless life was once involved. Not a place where life could survive, but evidence that life actually acted on the planet, changed chemistry, left patterns, and altered its environment in a detectable way. And now, for the first time, scientists believe they may have found exactly that. But this discovery sits on a knife's edge. In one future, it becomes the strongest evidence for ancient life ever found beyond Earth. In the other, it becomes one of the most damaging mistakes in the history of planetary science. Because if scientists are wrong about this, it won't just mean a flawed study or an embarrassing correction. It could redirect Mars research for decades. It could lock future missions into the wrong assumptions. And most importantly, it could quietly shape how humanity searches for life. Not just on Mars, but everywhere else in the universe. Because Mars is not just another planet. It is the reference point, the test case, the place where we are learning how to recognize life beyond Earth at all. To understand why this discovery is so risky, we need to rewind. Not millions of years, but to a single assumption scientists have relied on for nearly half a century. That assumption is simple. If you find certain chemical patterns in the right rocks, under the right conditions, life is the most likely explanation. On Earth, this logic works remarkably well. Living systems leave fingerprints. They favor certain reactions. They concentrate elements in unnatural ways. But Mars complicates that logic. On Mars, lifelike chemistry can be manufactured by physics. Ultraviolet light can break molecules apart and rebuild them into new ones. Perchlorates and other oxidants can scramble organics during heating. Even simple rock-water reactions can generate gases and carbon chains that look suspiciously biological from far away. So the real question isn't, can Mars make a biosignature? It's, can Mars make a biosignature without biology? Mars has fooled us before. Again and again, scientists announce discoveries that seem to point toward biology. Strange shapes etched into the rock, unexpected chemical ratios, minerals that, on Earth, almost always form alongside life. And again, Mars revealed another explanation, one that required no biology at all. Each time, the lesson was the same. Mars is exceptionally good at creating convincing imitations of life, because Mars is old, geologically complex, and capable of chemical reactions that Earth rarely produces on its own. The planet can fake biology in three main ways: by concentrating chemicals in the same spots, by repeating patterns through geology, and preserving those patterns for billions of years. Mars can do all three. What makes this discovery different is not just what was found, it's where it was found, and how it fits into Mars's ancient environment. The signal appears in rock layers that formed billions of years ago, during a period when Mars was warmer, wetter, and far more geologically active than today. These rocks were laid down when liquid water was stable on the surface, when energy sources were abundant, and when chemical cycles could persist for long periods of time. In other words, if life ever existed on Mars, this is exactly where you would expect to see its fingerprints. What scientists are seeing on Mars right now behave like something life would produce. It forms repeating patterns. It appears in clusters rather than randomly. It follows chemical rules we usually associate with biological processes. On Earth, signals like this almost always trace back to life. That's what makes this moment so compelling and so dangerous. But Mars is not Earth. Here's what makes Mars's evidence uniquely frustrating. Most of the gold standard life tests are impossible with a rover. A rover can detect organics, minerals, textures, and broad chemical families, but it struggles with the details that separate biology from geology. Exact isotopic ratios, subtle molecular handiness, and complex chains that reveal how a molecule was assembled. On Earth, biology often prefers one-handed version of a molecule over the other. Geology usually makes a messy mix. That single clue can collapse an entire debate, but it requires instrumentation and cleanliness standards that are extremely hard to achieve on another planet. And even when you do detect organics, you have to ask a brutal question. Are they ancient Martian chemistry or contamination that hitched a ride from Earth? That's why sample return is so powerful. You can run dozens of tests, repeat them, cross-check them, and let independent labs argue in public until the answer survives every attack. And here's the part that's making some scientists deeply uneasy. These signals can also be produced by purely geological processes, under conditions we don't fully understand. Extreme temperatures, unusual mineral combinations, chemical gradients that persist for millions of years. That means evidence sits in a dangerous gray zone. If the signal is wrong, there may be no way to prove it anytime soon. Because rovers can only do so much. They don't have a full laboratory. They can't run every test. And the most definitive tools we have, bringing samples back to Earth, takes years, sometimes decades. Space missions don't just follow discoveries. They follow interpretations. Where to land, what instruments to build, what questions to prioritize. Once billions of dollars are committed, those interpretations harden into strategy. And changing strategy in space exploration is slow, expensive, and politically difficult. If this interpretation becomes the foundation for future Mars missions, it may quietly become unquestionable, long before we actually know whether it's correct. The real risk isn't that the discovery is wrong. Science is built to survive mistakes. The danger is that it might be almost right. Because explanations that are almost right are the hardest ones to challenge. They feel good, they fit expectations, and they quietly reduce skepticism. And here's the trap. teams start optimizing instruments for that interpretation. Future papers cite it as an established context, and funding decisions get built around it. Even if doubt remains, momentum becomes its own form of certainty. If this interpretation later turns out to be flawed, the damage won't be dramatic. There won't be a single moment of failure. Instead, it will unfold slowly. Years of missions designed around the wrong assumptions, billions spent chasing the wrong signals, entire scientific careers built on an interpretation that slowly collapses. And the worst part? The public won't see the collapse as science working. They'll see it as the space agency's crying wolf. That trust is hard to win back. By the time we realize the mistake, Mars research may already be locked in. And yet, this is also what makes the discovery so powerful. For the first time, we're no longer asking whether Mars could have supported life. We're asking whether we're interpreting the evidence correctly. That shift alone marks a new phase in planetary science. Because this is what maturity looks like. We're hunting not just for interesting stuff, but for signals that survive hostile skepticism. The search for life beyond Earth has never been about certainty. It has always been about discipline. Knowing when to be excited and knowing when to slow down before excitement becomes assumption. Mars is forcing us to confront how easily we want the answer to be yes. And it's a rehearsal, because Mars is the easiest place to fool ourselves. If we can't stay disciplined here, we will misread signals on far more exotic worlds. Icy moons, ocean planets, and even exoplanets, where we don't get a second look for decades. In science, being completely wrong is survivable. Being almost right can be far more dangerous. Because the universe doesn't reward us for wanting something to be true, it only rewards us for being willing to question ourselves when the answer feels almost perfect. Mars is testing that discipline right now. And if the signal holds up, it changes everything. Not because it proves life in one headline, but because it gives us a reliable way to recognize life when it's subtle, ancient, and hidden in stone. So what should scientists do with a signal like this? They don't declare victory. They build a decision tree. First, look for the same pattern in multiple locations. Second, test whether the pattern correlates with water-altered minerals or with purely volcanic chemistry. Third, search for accompanying clues, textures, mineral contexts, and chemistry. That should travel together if biology is involved. If the signal survives those checks, then the priority becomes simple. Get the right samples, from the right layer, back to Earth. Because the final referee isn't a headline, it's replication. If you want to understand how discoveries like this shape not just Mars research, but the future of space exploration itself, this is exactly what we break down here. Because in space science, the most important discoveries are often the ones we hesitate to celebrate.